Hello, everyone, and welcome back. We're moving on with Chapter 8, talking about volumes. And now this lesson, you're going to talk about a different technique with washers. Now, let's recall what you learned. So I know this video is talking about washers, and you're like, dang, we even learned a technique. We've just been doing volume. You knew that. What you learned is you learned volumes of, and all of this is called volumes of revolution. Volumes of revolution with cylindrical discs, with emphasis on the word disc. So you've actually learned the disc technique. And what that is that for a given curve, arbitrary curve, so here's an arbitrary curve f of x, and it's bounded, say, a to b. So we're looking here, and say we rotate about the x-axis. All right. What you end up getting here is the volume, the exact volume found by doing the integral from a to b, as that's going to add up things, infinitely many things. And what you're going to add up are the cylinders that make up this space, because the idea is you would have a rectangle, and when you rotate that rectangle around, we end up getting a cylinder, where the radius of that cylinder is the function itself, f of x. As you can see that there, where if you rotate this about, this whole thing comes around like so. That was an awful picture. I'm sorry about that. That did not look good at all. Rotate this towards you, and end up getting this cylinder, and I can't really redeem it now. It's pretty messed up. Focus on this picture over here. We got a cylinder where the radius is f of x. But I was trying to show you that this right here would be the radius, because that's the center of the cylinder, of that circle there. And then the thickness of all of them is dx, infinitesimally small with x. So what you end up getting here is the volume is a to b of pi times your radius, which is f of x squared dx, because that would be your pi r squared h of your cylinder. Now, typically in books, they'll write it where they pull the pi out, and they'll just do this right here. Okay. So that was your volume of a cylindrical disc. Now, what we're going to be talking about today is washers. Okay. Now, maybe you're not familiar with what a washer is, but this is a washer. All right. And they typically use it with screws and nuts and bolts. But anyway, you can see that it's basically a cylindrical disc. And by the way, I don't think I've said this. Why is it a disc and not a cylinder? And I think I said it in the first video. It's a disc because it's a more or less a very skinny cylinder. So we don't quite call it a cylinder. It has a special name, and its special name is a cylindrical disc. Okay. That's all. So a washer, if you've seen it in your house, construction, building anything, is it's a cylindrical disc, but with a hole in it, right? So a washer, it's your cylindrical disc, but with a hole in it. Now, let's see a problem where it arises. So let's say, an example, let's find the volume of the region bounded by y equals x, y equals root x, and we're going to rotate about the x-axis. Okay. So what we have here, if I draw this, is y equals x, looks like so, and root x, and I'm going to exaggerate a little bit just so we have a bigger area here, would look something like this. I know it's quite a bit closer, but it would look something like this. All right, so there's root x, there's y equals x. All right. And we're going to rotate about the x-axis here. So it's this region right here. Okay. Now notice if we try to use the disc method and say we draw a rectangle, so let me zoom in. by hand. Where here's 1, and they cross at 1, 1 here. Okay. And we're rotating about x, the x-axis. So if I drew a rectangle that fills up the area between the two curves, like so, okay. And I pull this rectangle out and we study it, okay. Well, notice the idea is if we rotate this around the x-axis, what you're going to end up getting here, do my best to draw it, is it's not going to create a perfect cylinder. What you end up getting here is a washer, just like I have here, because of the hole that gets created. Because again, the volume that's being found is all of this right here gets rotated around. Okay. So how would we go about this? Now let's say we didn't know this technique and it'll come naturally out of it. So to find this volume, maybe what we can do is we can do the volume of just root x. So I redraw this picture just so you can see it a little bit. 1, 1. So if we want this region, maybe what we'll do is we'll find the volume of just root x using the cylinders. All right, so imagine taking the volume of all of this from 0 to 1. So we'll do the volume, and we're going to do with cylinders. And then we're going to minus the volume of just x, which of just x, if we focus on that, here's x in green, y equals x. If we rotate that around, what you end up getting actually is a cone. If you rotate around, you end up getting a cone there. So we'll do the volume here is going to be volume using cylinders minus the volume of the cone. All right. So let's do the math here. The volume using cylinders is going to be volume equals, so if we pull out one of the rectangles here, here it is the height is root x, the thickness is dx, so it's going to be the volume from 0 to 1 of pi times radius squared times your height, or thickness dx. And then we're going to minus the volume of the cone, which would be, if we use integrals, which we could do integrals, by the way, it would be 0 to 1 of pi, your radius is x squared dx. Now do note that we could have just done the volume of the cone using the formula, where the formula is 1/3 pi r squared h, really because it comes from 1/3 of a cylinder. Well, the radius of this cone here is x. So what we end up getting here, well, in this problem, the radius is actually 1. In this problem, radius is not x, it's 1, because we're going from 0 to 1. So the volume ends up being 1/3 pi x squared, and your height of this cone is 1 as well. The height of this cone is 1. Okay, so if I plug that in, it's going to be 1 squared times 1. So what you could have end up doing here is just we'll get pi thirds. Okay, but we'll do it with the integral just to show you that those are the same thing. So if we do this out here, we'd have volume equals, bring the pi out, and it'll be 0 to 1 of root x squared, which is just x dx, minus pi 0 to 1 of x squared dx. Doing the math now, we get pi times x squared over 2 from 0 to 1, minus pi x to the third over 3 from 0 to 1. And you can see here we'll get pi times 1/2 And then you do get minus 0 over 2. I'll just write it out as we're learning this. Times 1/3 minus 0 over 3. And notice the volume of the cone is that pi over 3, which is what we got using the formula. But we end up getting here pi halves minus pi thirds, which will simplify to 3 pi 6 minus 2 pi 6, which is equal to pi 6 units cubed. Okay. And that works. But could we have done this maybe faster where you don't have to separate the two integrals and consider the outer minus the inner? And we could, and that is using the washer technique. Right? So what's the washer technique? And I want to try and stick with it on this page. Is if you picture up here, if we look at this picture, when we have the washer, it looks something like this. Some height, like so. Right? Well, what's the volume of a washer? The volume of a washer, similar to how we did the volume using like breaking up the outer minus the inner, would be the volume of the entire thing as if it were just a cylindrical disc, which would be pi r, I'm going to use capital R is the outer radius, be pi r squared h, and then you'd minus the inner volume, which the inner volume there would be pi little r squared h, where that would be your inner radius. Okay, so writing it a little bit down, writing it down here, the volume of a washer, of one washer, is going to be pi big R squared h minus pi little r squared h. Okay. Now, if I picture this disk, see my best if I can redraw it here. Give it a little bit of thickness where it does have a hole there. Okay. Well, what's the big radius? Well, let me do this even. The height of this washer is dx, because remember it's that infinitesimally small thickness, your height or thickness. Now, your outer radius, notice that the outer radius in our problem, do it up here, the outer radius from the outside to the middle is root x. So our outer radius is going to be root x, and our inner radius here is the function x, or the inner radius from there to the middle is y equals x. Now, before I just plug this into the formula, I'm going to clean this up a little bit to help you see a nicer version of this. Since these two terms both have pi and h in it, I'm going to take those out and say pi h big R squared minus little r squared. And then that's the volume of one washer, where if I put this into the formula, the volume of the entire bounded region, it's going to be the integral where we're going to add up all the washers from, and in this case, it is, what is it from 0 to 1. Now, I can write it as pi h r squared minus r squared, where that's going to, fill it out. Now, let's plug in everything we know. What we end up getting here is 0 to 1 pi. Now, what's the height? The height of this is dx. And then your outer radius squared is square root of x squared minus your inner radius, which is x squared. And there it is. Now, cleaning up, we always just put the dx on the outside. So what we end up getting here is this is equal to, and I'll bring the pi out as well, pi 0 to 1 of square root of x squared minus x squared dx. And that's your volume of a washer. Now, doing the math here, probably gonna need a paper to bring this in, is we're gonna end up getting, bring this down, this equals pi times 0 to 1 of, and I'm just gonna write, that's gonna make x minus x squared dx. So calculating this, we'll get pi. The antiderivative is going to be x squared over 2 minus x cubed over 3 from 0 to 1. Plugging that in, we'll get pi times 1/2 minus 1/3 minus, and just in case if this was another number, notice I'm putting parentheses around it, be 0 over 2 minus 0 over 3, which we get pi times, and simplifying 1/2 minus 1/3, well, that's 3/6 minus 2/6. And notice how you get pi 6 units cubed, which is the same thing we got using the old method. Okay, so that's the washer technique. And let me summarize that, and then we'll look at one more example. So in summary, the volume with cylindrical discs is volume from A to B of pi times your, really it's, I hate summarizing this because I don't want you to just, I don't want it to be black and white. You need to, anytime you do these problems, you know, draw a picture, draw a cross section, and label. And then from there, you can try to find the volume of the cross section, which will help you with the volume of the entire closed region. The closed region. Now, the volume of a cylindrical disc then would be pi times your radius squared. So I'm just going to keep it as r squared h, which does become a to b pi. Typically, it's your function f of x squared dx. And then how does that relate to the volume of washers? And they would actually also be called cylindrical, but people just focus on that, the shape outside of that. It would be volume equals a to b of pi, and then it'd be your outer radius squared minus your inner radius squared, because that makes up your radius, times your height of that washer. Now clean that up a bit. It would be a to b pi r squared minus little r squared dx, typically, if it's rotating about the x-axis. Now let's look at one more problem and be done with this. Last example, let's do y equals x squared, y equals 5, and x equals 0, with those three functions, and rotate about the x-axis. So let's draw the picture. We have x squared. Now x equals 0 is this line here, so I'm not going to draw all of x squared. Y equals 5, 1, 2, I'll approximate it. It's not going to be perfect. That's approximately y equals 5, and x squared would look something like this. There's x squared. And the region bounded by those three functions is this region here. And we're going to rotate about the x-axis. So if we rotate this towards us, we'll end up getting a shape that looks something, I don't even know what that would look like. Rotate about it. That would be an interesting shape, wouldn't it be? It's going to look something like that, and then rotate it around, so almost have that inner loop there. Very interesting looking design. All right, so here we go. Draw a cross section. Label the cross section out here with its dimensions. So the radius here, this cross section is, your outer radius is 5. Your inner radius is going to be x squared. So this is going to end up becoming 5 squared minus x squared, because again, outer radius squared minus your inner radius squared, as this gets rotated around to make this disk. Way down here. Okay. And the height of these, the thickness will be dx. So writing your volume, we're going to have the volume is equal to, now what is it going from? It's going from 0 to, and what's that point? Now we could say when's x squared equal 5 and solve for x, which is root 5, which is great, and we'll do that. So the volume is going to go from 0 to root 5. Now if you wanted to, you could use a calculator for this, where let me put these functions in and say x squared and y equals 5. And then what you can do on a calculator, because sometimes maybe you don't want to cross it nicely, is use the calc feature and say calculate the intersection point between x squared, the second curve, and I want to guess that intersection point, and then you'll get your intersection point. Now 2.236 is the root 5. We'll stick with the exact here. And time is going to be pi times the outer radius squared, which is 5 squared, minus your inner radius squared, which is x squared, times your thickness dx. I'll pull the pi out. So you get 0 to root 5 of 5 squared minus x squared dx. And then we'll calculate this by hand and get pi times, that's going to give the antiderivative 25x minus x cubed over 3, valuing from 0 to root 5. Going to get a bit complicated, isn't it? Pi times, let's see here, 25 root 5 minus root 5 to the third over 3, and all that just going to be minus 0 if you plug 0 into all of that. So then what we end up getting here is multiplied by 3 over 3, we'll get pi. This will become 75 root 5 over 3 minus, that will end up making 5 root 5, because root 5 times root 5 times root 5 would be 5 root 5 there, over 3, which simplifies our answer to being 70 root 5 over 3 pi units cubed. And there's the volume there using the washer technique. Now, check it on a calculator, make sure we did it right. Let's see. Let's do math function integral, not in this screen. Math function integral from 0 to root 5 of, and that's, in this case, I'll put pi in it this time. Pi times your outer radius squared minus your inner radius squared dx. And hopefully we get that, which is that what we got? Let's see, 70 root 5 divided by 3, and then timesing by pi. And yes, it is the same thing, so we're good to go. Okay. So there it is, volume by washers. There's my summary and my notes on how to go about these. Okay. Hope that helps. If you have questions, be sure to stop by office hours and ask, or talk to your friends and make sense of it that way. Okay. Take care. Hope that helps. Bye-bye.